Galaxies are giant groups of stars, gas, dust, and dark matter that are gravitationally bound. They are like islands of light in the sea of the sky, glowing with the power of a billion of stars. They form when the primordial gas from the Big Bang cools down and collapses, forming bigger and bigger structures. We have several questions about this process, but we know that the current state of the galaxy can tell us a lot about how these structures are formed at a greater scale. One of the features that can reveal a lot of information is its orientation. The orientation of a galaxy is basically where its axis of rotation is pointing at, and having enough statistics of this quantity could show us the underlying patterns that the primordial fluctuations imprinted in the universe. As the universe has billions of galaxies, and the number of them that can be observed is getting larger with the development of new and powerful telescopes, we need a way to automatically and reliably extract this kind of information. Using the power of deep neural networks in object detection and image processing, we have developed a method to predict the orientation of a galaxy, just by looking at a raw image. But how to train a network to detect the orientation of galaxies if we do not have enough data in the first place? Well, to solve this issue, we choose to train our network using simulations, in particular the Ni-Hao one, that consisted in simulating 100 galaxies. These zooming simulations reproduce with high fidelity the behavior of galaxies and its rotation curves, and can be used to mock real observations. The orientation in the real universe is described in the 3D space, but to reduce the complexity of our problem, we choose our output to be a 2D projection of the 3D angular momentum vector in the image plane. Once we have rendered the data, we can focus on the neural network. We chose a convolutional neural network that consists in applying a series of convolution or filters to the image. We apply the convolutions pixel to pixel, extracting in each neuron different information. In the first layer, we extract edges and corners, then apply more convolutions to that results to obtain high-level features that are more difficult to interpret and contain information about the overall shape. We then end up with a general knowledge of what the orientation of a galaxy means and how we can extract it from an image. As developing a complete convolutional neural network is a hard process, we have used an already existing network. AlexNet and ResNet were the two selected ones. Since our problem is different from the usual classification tasks performed by this kind of networks, we adapted the existing networks to do this job, although the opportunity was so good that we could not resist developing a few new custom models to compare. Now that we have the motivation, the model, and the data, it's time for some training. But wait a minute, to train, you need someone to teach you how you are doing, right? Well, for neural networks, works the same way. We need a function that tells us how wrong are we doing our predictions in order to learn. This is the cost function, and it has been a key part of the project since we do not use the classical categorical approach. We need to implement functions to compare how far our prediction is from the ground truth. This has been achieved with the cosine similarity function. The cosine similarity function even allows us to take into account the degenerate solutions. First, we train our model on a CPU cluster. Then, we change to a GPU accelerated system that has 4 different NVIDIA Voltage 100 GPUs on each node, and it's run by the IT for Innovations group that made the training process 5 times faster. Although we faced some problems as the parallelization in 4 different GPUs presented new challenges, and to be honest, at first it felt like I was getting a Ferrari without even know how to drive properly. But after some trial and error and fixing some bugs, the training showed quite promising results, with the lowest accuracy being on the galaxies that are more rounded and has less clear angular momentum. Well, now we have a really cool model in a really huge computer, and that's it? No. Cutting-edge science requires solutions on an-edge devices. We have prepared the model to run in the most resource-constrained device we can get, even maybe less powerful than a regular smartphone, a Raspberry Pi. We installed an operating system, installed TensorFlow Lite, and the required libraries, enable SSH connections, and we have now a running model with a couple million parameters on a device that fits into your pocket. How awesome is that? The summer of HPC has been an amazing and intense journey of discovery and learning. We have been from creating the dataset in a supercomputer to running our own model in an edge device, growing through the process of planning and training some of the more complex models that the computer science has ever created. But for me, was just the beginning of the exploration of the wonders that HPC has to offer. Thank you.